Technical College, Engineering Science 1. The topic of discussion in this lecture is angular motion, and this is part 2. To present it, your lecturer, Mr. Shela B. Of angular motion with constant angular acceleration. The equation of angular motion below holds true when the axis of rotation is fixed. So below are the equations. Omega 2 is equal to omega 1 plus alpha t. B, theta is equal to open brackets omega 1 plus omega 2 divided by 2 times t. C, theta is equal to omega 1 times t plus half times alpha times t squared. D, omega 2 squared is equal to omega 1 squared plus 2 times alpha theta. E, theta is equal to omega 2 squared minus omega 1 squared divided by 2 times alpha, where theta is angle turned through in radians, and t is equal to time in seconds, and omega 1 is initial angular velocity in rad per second, and omega 2 is final angular motion in rad per second, and alpha is angular acceleration in rad per second squared. Okay, now let's look at the relationship between linear motion and angular motion. Let us consider a flywheel of radius r meters to be rotating about point O. On that diagram, point O, with uniform angular motion omega in rad per second as shown. Okay. Now the linear velocity v in meters per second of a point on the rim of the wheel will always be directed along a tangent at right angles to the radius of the point. Now let the initial position of the point be A, and after time t seconds let it be at B. The radius OA will then turn through an angle theta, which is equal to omega t in rad. So in this time, the point will have moved from the arc AB of length S is equal to r theta, and S is equal to r times omega times t. Now the linear velocity of the point on the rim of the flywheel will be given by linear velocity is equal to distance moved over time taken. So v is equal to s over t, which is equal to r omega t times divided by t. So now here v will reduce to r times omega, which is the linear velocity, which will be given as radius times the angular velocity. So the change in angular velocity w will produce a change in linear velocity. So now that equation v is equal to r times omega, it simply means that the change in angular velocity, which we are calling omega, will produce a change in linear velocity v. Now in a similar relationship rather exists between linear acceleration and the angular acceleration. So angular acceleration, which is alpha, is equal to, we're saying we're saying similar relationship exists between linear acceleration and angular acceleration. So linear acceleration is equal to r times the alpha which is linear acceleration, is equal to radius times the angular acceleration. Let's look at now the relationship between linear motion and angular motion in terms of equation. So linear motion equation, we have v is equal to u plus at. On angular motion there we have omega 2 is equal to omega 1 plus alpha t. And then b on linear motion we have s is equal to, which is the displacement, is equal to initial velocity plus final velocity divided by 2 times the t. There we have angle 10 through, which is the theta, is equal to initial omega plus final omega. Okay, which will mean initial angular velocity plus final angular velocity divided by 2 times the t. And then C on the linear motion we have displacement, which is s is equal to initial velocity, which is u times t plus half at squared. And there we have theta, which is standing for angle 10 through, is equal to omega 1, which is initial angular velocity, times t plus half alpha t, which is alpha standing for angular acceleration, times the time. And then here we have v squared is equal to u squared plus 2as. And there we have omega 2 squared plus omega 1 squared plus 2 times alpha times the theta. And then E on the linear motion we have s, which is displacement, is equal to v squared minus u squared over 2a, which is that a standing for acceleration. And then on the angular motion equation we have E is equal to theta is equal to omega 2 squared minus omega 1 squared divided by 2 alpha. So this is how linear motion relates with angular motion in terms of equation. So here what is changing are just the signs, but if you follow it close you find that they are just one and the same, but what is changing there is just the signs. For example, for the first one there, where we have the first a, where we have v is equal to u plus at. The v there on linear motion, when it goes to angular motion, is changing as omega. That is omega. And then the a there on the, we're still looking at the first equation, the a there is standing for acceleration, there is standing for angular acceleration. So what is actually changing are just the letters which are changing. Okay. Let's look at the example 1. A wheel rotating at 5 rad per second accelerates at 0.5 rad per second squared for 30 seconds. Find A, angular velocity after 30 seconds. B, the angle 10 through by the wheel during this time. So 1A, omega 2 is equal to omega 1 plus alpha times t. So that omega 2, which we are saying final angular velocity, is equal to, we plug in for initial angular velocity is omega 1, 5 rad per second, plus the value for angular velocity, angular acceleration, 0.5 rad per second squared, times the value of t, which is 30 seconds. When you compute that, it will give us 20 rad per second. Okay, part B, we have the angle 10 through by the wheel during this time. Okay, so now there, what we are going to do is that we're going to apply that formula. Theta is equal to initial angular velocity times t plus half times alpha times t squared. So theta is equal to, open brackets, we plug in the value for initial angular velocity, which is 5 rad per second, times the value for t, which is 30 seconds, we close brackets, plus half times, open bracket, 30 seconds, close brackets, then we square. So we compute that, it will give us theta is equal to 375 rad. That is for part B. Question 2. A grinding wheel has a diameter of 200 millimeters. If it rotates at 2,100 rev per minute, what is the circumferential grinding speed in meters per second? So there, we are going to use that formula, which according omega is equal to 2 pi n divided by 60. Now, the number of revolution, or n, is given in rev per minute, which is 2,100. So they are going to multiply to say omega is equal to 2 pi times n, which is 2,100 divided by 60. Because it is rev per minute, we are going to divide by 60. When we compute that, it will give us 220 rad per second. Now, the circumferential grinding speed is the same as tangential speed of a point on a peripheral of the wheel. Hence, that V, which is circumferential grinding speed, is equal to R times omega, which is equal to, we substitute for R, 0.1 meters. Now, that R is 0.1 meters. How has it come about? We have been given the diameter 200 millimeters. So now that 200 millimeters, will take it to meters. Now how do we take it to meters? We divide by 1,000. So we divide 200 meters by 1,000 to give us 0.2. And that 0.2 meters will be the diameter. Now since you are looking for the radius, we divide by 2, which will give us 0.1. So 0.2 divided by 2 to give us 0.1. That will be the radius. So 0.1 times 220 rad per second, it is equal to 22 meters per second. Example 3. The road wheels of a motor vehicle increase their speed uniformly from 50 rev per minute to 1,100 rev per minute in 40 seconds. A. Calculate the angular acceleration. B. If the diameter of the wheels is 0.7 meter, what is the linear acceleration of the point on a tire? So let's go to solution for 3A. Okay, so the 3A there, we have going to have, first of all, we are going to change those number of those, we're going to change n, rather, so we're going to change the angular velocities which have been given in rev per minute to rad per second. So changing omega 1, which is the initial angular velocity, will give us 2 pi n over 60. So 2 pi times n, which is the number of revolution in rev per minute, which is 50, divided by 60, and our answer will be 5.24 rad per second. We have omega 2, which is final angular velocity, is equal to 2 pi n divided by 60, which is equal to 2 pi times the n, which is 1,100, divided by 60. When you compute that, it will give us 115.2 rad per second, which is 115.2 rad per second. Let's further, because we're looking for angular acceleration. So alpha there, that is now the formula for angular acceleration. Alpha is equal to final angular velocity minus initial angular velocity divided by t. We plug in the values for a final angular velocity, which is 115.2 rad per second minus 5.24 rad per second divided by 40 seconds. And our answer will be 2.75 rad per second squared. Okay. Now for part B, we're saying if the diameter of the wheels is 0.7 meter, what is the linear acceleration of the point on the tire? So linear acceleration is equal to radius times the angular acceleration. Plugging the values for radius and angular velocity. Radius is 0.35 meters. Why is it 0.35 meters? The diameter is given in 0.7, so we're looking for the radius. We divide 0.7 divided by 2, and we're going to have 0.3 meters. And then we multiply by angular acceleration, which is 2.75 rad per second, and when we compute that, it will give us 0.9625 rad per second squared. Okay, let's look at question 4. A wheel is rotating at 2000 rev per minute, and when a brake is applied, the wheel is brought to rest with uniform retardation in 400 revolutions. Find A, the time taken to bring the wheel to rest. B, the angular retardation in rad per second squared. Again there, we are going to, we have been given the angular velocities in RPM, which is rev per minute. So we have to change that to rad per second. So changing omega 1, which is initial angular velocity, we're going to say angular velocity is equal to 2 pi n divided by 60, and then which is equal to 2 pi times 2000 divided by 60, and our answer will be 209.4 rad per second. And final angular velocity is equal to 0 since the wheel is brought to rest in 400 revolution. Hence, angle 10 through will give us 2 pi times the number of revolution, which is equal to 2 pi times 400, which will give us 2513 or 2513 rad. So that is the angle 10 through that to be given. So now we are looking for time, so use that the formula theta is equal to open brackets initial angular velocity plus final angular velocity divided by 2 times the time. Plugging in the value for the theta, which will give us 2513 rad, is equal to open brackets 209.4 rad per second plus 0 rad per second divided by 2 times the t. Making t the subject, it will give us t is equal to 2513 rad times 2 divided by 209.4 rad per second, which will give us 24 seconds. That is for part A. We are done. Now for part B, we have that formula where we say final angular velocity squared is equal to initial angular velocity squared plus 2 times alpha times theta. Substituting the value for final angular velocity, we're going to have 0 is equal to 209.4 rad per 209.4 rad per second, and then we're going to square that one plus 2 times the 2513 rad times the alpha. Making alpha the subject, which will give us alpha is equal to 43848, or 43848 divided by 5026. It will give us negative 8.724 rad per second. Rad per second being our angular retardation in rad per second squared. So for today, we are going to end here. Thank you for attending the lecture. See you in